Every single day your body quietly says goodbye to nearly 150 billion cells. This isn't a sign of sickness, quite the opposite. It's a sign that your body is alive, aware, and constantly renewing itself. Through a carefully controlled process, old, damaged, or unneeded cells are cleared away, making room for new ones. This balance is vital for health, and the mechanism behind it is known as regulated cell death, RCD. Most people are familiar with apoptosis, the well-known programmed cell death that unfolds like a silent, clean exit. But cell death comes in many forms, some explosive, some fiery, and some still mysterious. One of the most fascinating and recently discovered among them is ferroptosis, a kind of death driven by iron and oxidative stress. Let's dive into its story. In 2012, scientists officially named a strange, iron-dependent form of cell death, ferroptosis. It wasn't caused by the usual suspects like caspases, the enzymes behind apoptosis, nor did it resemble necrosis or pyroptosis. It was unique, a slow, oxidative meltdown where iron and lipid peroxides build up inside the cell until it collapses from within. Although researchers had previously observed something similar, like oxytosis in neurons back in 2001, only in recent years have they pieced together how this form of death really works. At its core, ferroptosis is about imbalance. When too much free iron accumulates inside a cell, it reacts with lipids in the cell membrane to form toxic lipid peroxides. These peroxides weaken and damage the membrane, eventually causing the cell to rupture and die. Let's zoom in on a real-world example. Parkinson's disease, PD. In PD, certain brain cells, especially those involved in movement control, start to die off. Researchers believe ferroptosis plays a critical role in this process. Here's how. Inside neurons, iron levels begin to rise. This iron sneaks in through transferrin receptors and metal transporters, while the iron export system, via ferroportin, becomes unstable due to malfunctioning proteins, like the amyloid precursor protein. As a result, iron starts to pool in dangerous amounts. This excess iron reacts with cell membrane lipids, especially when enzymes like ACSL4 and lipoxygenesis, LOXs, are active. The result? A buildup of lipid hydroperoxides, toxic molecules that corrode the cell from the inside. Normally, cells defend themselves with an antioxidant enzyme called GPX4, glutathione peroxidase 4, which turns these dangerous peroxides into harmless lipid alcohols. But GPX4 needs glutathione, GSH, and GSH depends on a steady supply of cysteine, an amino acid brought in through the XEE antiporter. When this system fails, whether by blocking cysteine or inhibiting GPX4, lipid peroxides spiral out of control. The membrane breaks, the neuron dies. In lab models of Parkinson's disease, scientists saw that GPX4 depletion led to massive cell membrane damage, triggering a ferroptotic chain reaction. Here's where things get exciting. A protein called ferroptosis suppressor protein 1, FSP1, emerged as a powerful ally. FSP1 helps recycle coenzyme Q10, CoQ10, which can trap and neutralize lipid peroxides, stopping ferroptosis before it starts. Other compounds like leproxtatin 1, ferrostatin 1, and vitamin E derivatives are being explored as potential ferroptosis inhibitors, especially for conditions like Parkinson's, where preventing cell death is key. But in cancer, ferroptosis becomes a weapon. In Parkinson's and other neurodegenerative diseases, we want to block ferroptosis to protect cells. But in cancer, it's the opposite. Cancer cells often become immortal. They find ways to avoid dying, even when they should. Researchers discovered that inducing ferroptosis in tumor cells, by inhibiting GPX4 or blocking cysteine uptake, can push these stubborn cells toward self-destruction. This makes ferroptosis a double-edged sword. In some cases, it's a disease-driving process we want to stop. In others, it's a potential therapeutic strategy we aim to trigger. Ferroptosis is no longer just a scientific curiosity. It's emerging as a central player in a wide range of diseases: Alzheimer's, liver disease, heart conditions, and even infectious diseases. It's mechanistically distinct from apoptosis, autophagy, and pyroptosis. And with every study, we're learning more about how to modulate ferroptosis, either to save precious cells or to target dangerous ones. Understanding this fiery form of cell death may help us unlock entirely new strategies in medicine. In the grand story of life and death, iron plays a hidden but powerful role. Too little, and our cells struggle. Too much, and they die. Ferroptosis reminds us that survival isn't just about staying alive. It's about knowing when, how, and why to let go. As science continues to decode this delicate dance, we may find ourselves not just understanding disease better, but learning how to write new endings to some of our oldest biological stories.